Welcome, everybody, to GlugNet. This month, we are pleased to welcome Joe Brinkman, who will be speaking to us on native cloud development. We also have Zoltan Lahosky back with us for another lightning talk. But first, before we do any of that, a few housekeeping items. A little bit about GlugNet. We are the Greater Lansing user group for .NET developers, based out of Okemos, Michigan, as pictured here on this map. Our meetings are free and open to the public and held every month on the third Thursday. The best way to find out more information about our meetups is to go to our meetup website, meetup.com/glugnet. We are always looking to have lightning talks as part of our presentations, like the one Zoltan will give us later tonight. If you are interested in giving a lightning talk, you can contact myself, Stephen Ball, or my colleague Joe Kunk, and we will get you slotted into a meeting. Tonight's presentation will be interactive, so we encourage asking questions or answering questions from our presenter. But we also want the ability to be able to hear all of the presentation. So we just ask that if you are not asking a question or answering a question, if you could please remain on mute. But feel free to jump off of mute and ask that question if you feel the need. At the end of tonight's presentation, we will have a survey to let our speaker know how his presentation went. All the feedback we collect is anonymous, so we would very much appreciate every bit of feedback you give us, good, bad, indifferent. We want to hear it all. At this point, we'd like to thank the sponsors for this evening. NIS Technologies, who is providing this go-to session for us. The .NET Foundation, who's paying the bills for the organization. And TechSmith, our normal in-person hosting site. We are in talks with them to hopefully get back real soon, but as soon as we know more information, we will share that. The meetings are recorded by Sam Nasser and posted to his YouTube channel. You can either use the QR code on the screen there, or you could go to youtube.com/@SamNasserMVP to find those recordings. And a few other additional meetups you might be interested in based on this meetup. Our friends in Cleveland at the C# VBNet user group, the Greater Lansing area for SQL Server, otherwise known as GLASS, a .NET study group, and if you are in the Southfield, Michigan area, there is an in-person only group, mi.net. So feel free to check out our friends if you are in those areas. Okay. So without further ado, Zoltan, I will make you presenter and you can start your lightning talk.
Awesome, thank you. So it's great to be back here again with something completely different because why I wanted to bring this topic about a CMS called Orchard Core here, because I think probably you are still reinventing the wheel when it comes to .NET web development. So let's try not to do that. Let's try not to do that with Orchard Core. Here's the tagline of Orchard Core. I won't read it because you can do it quicker, but let's dissect a little bit. So what is Orchard that I would like to show you here? Well, it's an open source project. That's pretty clear. It's also modular. So while an Orchard application by default is a monolith, within that monolith, there's modularization. There are a lot of packages, a lot of features that you can mix and match, use or not use, turn on, off, or whatever. And by the way, Orchard can be split into multiple services as well if you don't want a monolith to begin with. It's also multi-tenant. That means that from a single application, you can run multiple websites. That's pretty useful if you are hosting applications for your clients as well. If you run mini sites for marketing campaigns, that sort of stuff. And Orchard is an application framework and a CMS. It's the same thing, but some packages are about framework functionality and some packages are about CMS functionality, content management system, if the abbreviation is not clear for somebody. And it's built on ASP.NET Core, of course. Now, a couple more details. It actually targets .NET 6 and 7 both. It follows the MVC paradigm, but you don't have to. So in your application, you can do other things as well. It's open source under the umbrella of the .NET Foundation, just as this meetup, and it's a very active project with thousands of commits, hundreds of contributors, and a lot of issues that are actually being closed. So the issue tracker is not perpetually growing. The community is fixing bugs and implementing feature requests. Now, why I'm talking about it here is because I'm one of the core contributors of Orchard. I've been working with Orchard since more than a decade now, and with my business partner, we also founded a company born out of Orchard also about a decade ago called Lombic Technologies. We are since then grown into the largest Orchard team in the world and working with companies like Microsoft itself, or the Fortune 500 event organizing company Live Nation, or institutions like the Smithsonian Institution. Now, when it comes to CMSs, why you would use Orchard specifically? Well, first of all, we are talking about ASP.NET Core and optionally MVC, as I mentioned, but with a lot more stuff. So everything you know about ASP.NET Core and ASP.NET Core MVC still applies. It's not like you are creating an Orchard application, but rather you are creating an ASP.NET Core application and adding Orchard to it, what I will also show you in a minute. And Orchard adds a lot of features on top of that. For example, of course, content management. It's a very flexible, very extensible content model. But all the usual stuff that you need for every website and otherwise every web application, like user management, media management, workflows, audit trail, multi-tenancy that I mentioned. And one thing that's also quite important if you are more in the beginning of your career is that when you join such a big and quality open source project, you can become a lot better developer. This is also my personal story. I think I became a professional .NET developer after joining the community. Because, by the way, some people that work on ASP.NET Core itself also contribute to Orchard Core. And of course, there's also a community. We are not just talking about code. There are a couple thousand people active on GitHub. This is from our last in-person conference many years ago. Since then, we are mostly online. We also had our pretty large online conference a month ago. And a lot of talk until now, so let me show you a couple of examples of Orchard. This is a pretty simple website for a marketing campaign for a video game, but I just wanted to show you because you probably know the franchise Transformers. So sometimes well-known brands also use Orchard. Or otherwise big names like the Royal Veterinary College from the UK. And this site also has cat pictures, as you can see, so that's already makes it quite important. But Orchard is not just for static content websites. What we see here is the website of an airline that, apart from static content, also contains a booking feature, as you can see here. I mentioned Fortune 500 companies also use Orchard, like Live Nation. This is actually by Live Nation. It's their brand House of Blues, which is for event venues and pubs. Governments also use Orchard, like the city of Santa Monica of Greater Los Angeles also uses Orchard, or the federal government even, because the Smithsonian is part of the federal government. And their division, the Smithsonian Folklife, and also the Smithsonian Folkways recordings use Orchard as well. This is actually a pretty complex website with a huge music catalog, including streaming and shopping. But sometimes state governments also use Orchard, like the Employment Security Department of Washington State. And if you are interested in other examples, check out our site showorchard.com, where we collect those orchards websites that we find exemplary. The latest one is actually ours, because we just recently renewed our website. So now that we have seen the very basics, let's actually try Orchard out locally. So I will now switch to Visual Studio. And what I have here is a simple solution with 3 projects that I generated with the Orchard code generation templates. And kind of the root project here is this web project, which, as you can see, is a standard ASP.NET Core project. But what it makes use Orchard is that I added these 2 Orchard Core packages to it. Actually, this is the more important one. This adds all of Orchard. And I mentioned that Orchard is also a framework and a CMS. You don't have to use all of Orchard. You can just use some of the framework functionality or all the framework functionality, like localization, data access, logging, or you can use all of it with all the user-facing features, or you can just mix and match and select which features you want. But here I'm using the whole of Orchard just to be able to show it to you. And if we start this application, we'll get to the setup screen. That's kind of where all Orchard projects start. Now, let me set up Orchard here. You have to fill out a couple of details and select a recipe. A recipe is basically a JSON file that contains content and configuration of an Orchard Core app. You can use that to export and import content and configuration, and also to template sites like this. So you can create like a blog template or a company website template or a portfolio website template or a social application template or whatever you may think about. Here are a couple of other technical details, and let's also create let's also create our default admin user. I will use the very secure password, which is of course only for development. And once the setup finishes, which creates the application, creates the database, we see that this was the content of the blog recipe. It has a blog post here with some metadata and everything, and also an about page. So far so good, but let's actually check out the admin here. So I will log in with the same credentials here. And here we can already see that, well, here is the editor of our blog post. And yeah, it has a title, permalink, body, something that you would usually await from a blog post. One cool thing though here is this preview feature. If you open this preview, then you will get such a live preview on the right hand side that updates with every keystroke. So that's pretty cool if you like to check out how your content will look like in action. Now, Orchard, I mentioned, has a flexible content model, a flexible extensible content model, which is kind of in the core of the whole thing. What makes this flexible is its building blocks. Because if you check out this article on the right hand side, which is the about page, and the blog post, you can see that both of them has something called a title here, and also a permalink. Now, both of these content items here are built up from the same building blocks actually. And if you check out content definition and content types here, we can see the blueprints of these content items. A blog post here is the blueprint of this blog post content item we see on the left hand side. You could also think about it like on the right we see a class, and on the left we have an object of that class, an instance of that class. So here is the schema, the definition, the blueprint of our blog post. And as you can see, it has title part and outer out part. These parts are the building blocks of the Orchard content model. And that article, the About page, has the same parts. So this way, you have these little building blocks, content parts. You can use them to mix and match everything, to build new types of content, or you can also change everything. So I could remove title parts here or outer out part, and I could change what the blog post does. Now, we won't have time for it, so just to give you a little bit of idea of what else is in Orchard, but I won't be able to go into details. There's also media management, of course. There's search with Lucene and Elasticsearch. There's role-based access control. Here's the user account that we created during the setup. And by the way, this is a local user account, but external accounts can be connected as well with Active Directory, personal Microsoft accounts, Twitter, Facebook, Google login, everything you can imagine. There are, of course, also roles with a lot of permissions that you can select. So quite some granular role-based access control. The permissions, you can create your own. The roles, you can also create your own. So everything that I'm showing you here is just built in, but you can extend everything. Speaking of which, under features, you can see all the built-in features of Orchard that you can individually enable and disable. You can also create such features yourself called modules. And the other extension points here are themes, which are about the look and feel of the website. And actually, here's a demo theme that I will make the current one. And as you can see, I just made the site very ugly. Now, this theme is actually one of the projects that I generated here. And I just wanted to write a single line of code with you, so that's not left out. You create a theme, such a theme, to define the look and feel of the website. And basically, here is where you would put all of your CSS, HTML, or Liquid templates, and all of your CSS and JavaScript and graphics, that sort of stuff. So you write the code on the right-hand side, do a refresh, and it works on the left. Now, if you like to host Orchard, it runs everywhere where .NET runs, including IaaS, so Azure App Services is an option as well, and Docker, of course. You can also use our SaaS if you don't want to host it yourself. You can go to .NET.com, click, and you get a website in a multi-tenant app. It's much more limited, but still it's very flexible, and you don't have to worry about hosting. Now, if this little glimpse into Orchard was interesting for you, I encourage you to check out starting under the project homepage, or Orchard Dojo, where we have news, and also the Dojo Course 3, which is a video tutorial series. Or if you like to learn from code more than from videos, check out our training demo module. So that was it from me. Thank you very much. And if you like to start with Orchard, just let me know if you have questions.
Question, Zoltan. I'm not sure if you covered this before, but is it available on Azure?
Yes. Orchard is something that you usually build your application with or on top of. So it's not like that you use Orchard as a user without doing development and hosting it yourself. And if you want to host it yourself, yes, it's available on Azure. You can deploy it to Azure App Services. You can deploy it as a container instance, or you can even deploy it on a virtual machine if that's what you like. Otherwise, the mentioned .NET SaaS, by the way, also runs on Azure, and it's otherwise integrated into Azure as well. So that's more like the lightweight way of starting with Orchard.
Great, thank you.
All right. Any other questions for Zoltan? All right. Well, thank you very much again for that talk. That was excellent. Joe.
Thank you very much.
Up to you.
Okay, awesome. Well, thank you. Well, thank you everyone for joining us this evening. I'm going to be doing a talk on cloud native development and what that really looks like in terms of development. We're not going to do a lot of demos. We're going to talk mostly conceptually because I think that's the most important part of cloud native development. And it doesn't matter whether we're talking about running in the Google Cloud, whether it's AWS, whether it's Azure, or some of their private cloud or other public cloud, right? As we go through tonight, feel free to interject, ask questions. This is more of a discussion than it is really just a one-way conversation. So feel free to join in. With that, a little bit about myself. My name is Joe Brinkman. I'm a director of consulting with Improving. I've been here about 4 years. Prior to that, I've been a project manager at Auth0. I was also a co-founder of DNN, so very familiar with Orchard. Have been competitors of theirs for many years, so our content management was a bit different in DNN. We're one of the originals in the .NET space, and that is a project that's still going strong today, although they don't support .NET Core. I've also been an author. I've authored a couple of books and have spoken internationally, primarily in North America, but a little bit in Europe as well. So a couple of things on the Improving side. So we're always looking for good people. If you know people who are looking, I know there's been a lot of layoffs recently. We've had some even inside of Improving, but we're primarily constantly on the lookout for great technologists. So if you know people who are looking, we're happy to at least talk to them and see if there's a good fit there. And we also offer training primarily in the Scrum area, but also in other technologies as well. So again, some good resources for people. Finally, for those who are here with us tonight, at all of our talks, so Improving offers gift cards for anyone who chooses to sign up and wants to take advantage of that. We picked someone from the presentation, so odds are pretty good given the size of the group here tonight for whoever wants to sign up for that. I'll post that again at the end of the talk, but with that, let's go ahead and jump on in. So we're going to talk a little bit about the history of cloud native application development. We're going to talk about the cloud, really dive into what it really means to be cloud native, and talk about some of the best practices or good practices. I hate to say best practices because they're constantly evolving. What is good today or what's recommended today, next year, 5 years from now, may not be the same thing. You see that recently with some of the changes that are occurring around microservices and some of the proponents of microservices starting to back away from those or backing away from them in certain scenarios, right? So the key here is really focusing on maybe some of the good recommendations or good practices we have today, and not necessarily this is what you should always do in every situation. So when we think about what computing has looked like over the years, right? We started with big, expensive computing resources, right? Versus these small, cheap resources that we have available to us today. The challenge with these was they were hard to replace, right? Versus if you look at some of these smaller resources, I can replace these sorts of stacks of resources fairly easily. If you go to some of the backplane computer services that you saw in the VM space, right? I can replace a single backplane in one of those in a virtualized environment fairly easy. Over the past 60 years, computer evolution has meant a constant reduction in size and cost while simultaneously providing for greater and greater performance. And that has caused us to really change the way we build computer solutions, right? Or software solutions. And so if you think about sort of this evolution, we started back in the 90s and prior, right, where everything was running on basically physical hardware. There was almost a one-for-one relationship between the physical hardware existed and the applications that we were running. And there was a single operating system, and for however many applications we ran on that single box, they all shared that common operating system, right? So we were kind of tied into this physical constraint around these resources. And those resources running on that box all shared those same, those applications running on that box all sort of shared those same set of resources. As we moved from the 90s into the 2000s, we started to see a rise of virtual machines starting in the late 90s on up into the 2000s, 2010s, right? And virtual machines epitomized by the likes of VMware or Hyper-V on Microsoft, or VirtualBox, or Parallels if you're running on Apple. All of these different virtual environments were ways that we could slice up large hardware systems into smaller and smaller slices to sort of give you this ability to run various workloads in these isolated environments, all sharing the same common underlying hardware resources, whether it was disk space or CPU utilization or graphics or whatever the resource was we were trying to share across these environments. And to each virtual environment, all of these resources looked like they were dedicated to that environment. We could allocate, we could have a 96 CPU machine and allocate CPUs to various virtual machines. But again, we started to get constrained by how many actual hardware resources were available within that one virtual machine host. And virtual machines, by the way that they were developed, were pretty well or used a lot of resources just in overhead in the virtual machine. As we roll into the 2010s and beyond, and where we're at in the 20s, we started to see the rise of virtualization at the operating system level through the use of things like containers. And those really freed us up in a lot of ways to to scale applications sort of differently than we did when we were in virtual machines, or the way we scaled when we were in physical machines, right? At the container level, I can have each container running maybe a different flavor of an operating system. One might be running Ubuntu, the next one might be running Alpine, another one might be running Debian, and another one might be running some flavor of Windows, depending on how we've configured our overall system, right? Containers give us some less secure, but still plenty adequate isolation between individual applications, and allow us to deploy fairly easily. And one of the differences as we start looking at these different technologies that we've had along the way is the way that we scale in terms of applications, right? And if you think about that, physical scalability, right? When you go back to those original mainframes, and you go back to some of the early days of computing, if you wanted to scale those systems, it was very difficult, right? Hard drives were room-sized devices. As we roll into the 70s and 80s, and some of the miniaturization that was going on, it became easier to scale, but there was still some high-end caps, or there were still some upper-end caps on how easily and rapidly we could scale. And if you think about our ability to scale when we're dependent on physical hardware, is comes down to our ability to get additional physical hardware to actually provide for that scaling. I go back to the server days in the 80s and 90s where scaling meant ordering a new machine from Dell or a new group of machines from Dell, bringing them in, spending time ghosting images onto those machines so that we could get a new operating system, a new configuration. And scaling was something that we did and often took weeks or months to properly scale applications, and meant we had long lead times on how we went about scaling. As we moved into the virtualization space, what we ended up doing was buying very, very large, beefy servers, but nonetheless, they were still these physical machines that were constrained to a maximum size. You might have machines with a couple terabytes of physical memory, and dozens, or in some cases hundreds of CPUs, or cores, I should say, is more adequately or more appropriate, and terabytes or petabytes of drive space. But ultimately, you were capped by how much you could physically fit inside this physical space as your ability to scale those VMs. As we move into containerization and start advancing into these new ways of scaling, we start finding different ways to scale, or we start doing things like doing replication and some of these other more advanced techniques that allow us to scale rather than scaling up by adding more and more hardware. Virtualization has allowed us to scale horizontally by adding another VM or adding another container or another 10 containers or 20 containers, whatever it takes to scale our application. And if we build that virtualization environment correctly, then we can scale almost infinitely because we become less dependent on the underlying hardware, and it's really around that virtualization layer that sort of hides that the actual hardware implementation details from us, right? And this is where the cloud comes in, right? Because the cloud fundamentally is a scaling solution. It's about how do I provide resources on a just-in-time basis to applications that need those resources. So one of the things to also understand is that as we've started to apply this virtualization, the cost for scaling actually goes down on a per unit basis. If you go back and think about some of those servers that we had in the 90s, I remember one time going in to interview for a company, and they had these massive servers that were redundant across every subsystem, whether it was the power supply or the graphics card or the CPU or the motherboards. There was multiple redundancies built into the server, and it was like a $1 million server, right? Like if I needed 2 of those, right, my unit of scale for cost was, okay, I need another $1 million. And if I just needed that for redundancy purposes, it's a huge jump to make that next investment. When we're talking about scaling at something like a container level, right, I might be talking about pennies per each unit of scale, or dollars per each unit of scale, rather than thousands, tens of thousands, or millions of dollars to scale my next unit. So that's why the way we build for cloud, the way we build for containerized applications in today's environment is really fundamentally different than the way we built in the 90s and 2000s, because our means of scaling has changed. So now, rather than throwing more hardware, which we call scaling up, we tend to focus on how do I just give me another unit of virtualized application space to run another node, and we call that scaling out, right? And so the other thing that this allows me to do is, because I can do this sort of on the fly, I can scale up very efficiently because the costs become almost equal to my usage. No longer do I have to over provision for resources because I know that in the next couple of weeks or in the next month or the next 3 months or 6 months, I'm going to need that next $50,000, investment, or I'm going to need that next $1 million machine, right? So I have to buy that ahead of time, leave it unused for months, and in the expectation that at some point in the future I'm then going to max out on that machine, and then make another $1 million investment, so to speak. Whereas the way we scale now, by scaling horizontally rather than vertically, scaling out rather than scaling up, it allows me to scale up just when I need to, and I've only invested a couple of dollars per unit of scale, so that I'm much more efficient with my spend. And if I need to no longer have access to resources, I can scale that back down, and again, keep my usage curve very, very close to my cost curve, right? So I'm never over provisioning, or rarely over provisioning resources, because I can easily spin more resources up very quickly. So why do we go through all this? What is it that the cloud natively provides to us, as opposed to maybe running our own containerization system or running virtual machines? What do we get with that cloud and the scalability and the way it scales when we run in a cloud native environment? So let's look at some of those core whys. Like, why should I consider the cloud? The first is scalability, right? And that is the ability of our applications to handle larger and larger loads, to deal with larger and larger data sets, to deal with more and more computation requirements, or to deal with larger and larger numbers of users, right? So scalability is one of the first things you see in the cloud, because if I need more resources, whatever that is, whether it's compute or storage or graphics processing capability, whatever that requirement is, it's fairly easy to spin those up within the cloud and scale out to however many resources I need for the particular application or the specific workload that I'm looking at. The second area we look at for the cloud, and why the cloud is so important, is around reliability. When we build applications in the old traditional models, we often had a single node, and if something happened to that server, it could take our application down. So we started building things in web farms, and we might have one node or 2 nodes or 3 nodes, whatever that looked like, right? And the costs scaled dramatically as we start adding all these nodes. But the application has to be built in a way that can take advantage of that. In the cloud, a lot of this adding more nodes happens sort of automatically, and we get that redundancy across all of the systems that we're deploying. So whether it's CPU or storage or access to I/O through networking, all of these systems have multiple redundancies built in at every level. So if one part of the system goes down, we can still have throughput, we can still have our CPU and our storage be unaffected or minimally affected, as opposed to being a complete outage, right? The third thing we look at is around elasticity, and we talked about that a little bit earlier. that elasticity curve, which is where we scale up and down resources as needed for the application and for the load that the application is currently under. And that elasticity allows us to keep the cost curve very close to the load curve, right? So we don't ever have to dramatically over provision our app in cases where the load just doesn't demand it. Often this means for applications, if you typically have an application that is used for a business, you might only provision resources during your normal working hours, maybe a couple hours either side, and you might turn off a lot of resources overnight when they're not going to be used. And maybe you spin up different resources overnight to handle batch processes and other background tasks that might be running overnight that you wouldn't normally run during the daytime, right? So maybe your load shifts to a different type of resource utilization. But again, you're spinning those resources up and down and very elastically, and the cloud is something that allows us to do that. And we write applications, more importantly, that take advantage of that. Oops. So, and the fourth area that we look at in terms of the cloud and why we choose the cloud and why cloud native is different than what is on-prem, and that has to do with security, right? A lot of times I've seen people build applications in a sort of that old server mentality, and the problem is we could only secure the application to the level that our own internal security teams had the experience and expertise to be able to do that. One of the benefits that the cloud and cloud native computing allow for is for security experts in these cloud providers to configure systems or configure those base platforms in a way that sort of give us security out of the box in the underlying platforms and give us a lot more security controls over how we can expose or hide various resources within the cloud to take advantage of the fact that maybe we don't want our database to be exposed to the outside world, right? I don't have to be a networking engineer and have nearly as much experience to be able to adequately secure my resources in the cloud as I might have on premise, where I had to have someone who was an expert in how to configure DMZs and how to configure my routers and how to configure my firewalls and some of the other things that I was running internally. Much more of that is available to everyone who is using those cloud platforms. It's not restricted nearly as much as it was in the past. So these four areas really are the heart of where the current cloud compute model is very, very different from the on-premise model and the old way of building out applications and how we scaled applications, how we secured applications, and they're a core part of understanding what it means to be cloud native, which is to build in ways that take advantage of how the cloud is fundamentally different than on-premise development or virtual machine development, even to some large degree. So several years ago, there was a foundation developed around cloud native computing, the Cloud Native Computing Foundation. And they set out to sort of identify how cloud computing and help organizations understand how cloud computing was different, how applications running in the cloud, you need to think about them differently and how you architect them, how you build them, how you operate them. And we really sort of look in these environments to a couple of key areas that I like to focus on. One is around how you build and run scalable applications. and how you do that in dynamic environments, how I can spin up and spin down resources as they're needed, or scale them out to whatever level is needed, right? Where I can maybe in today's environment, it's not uncommon for me to see a check-in happen within an environment to during that build pipeline to go out and spin up some resources in the cloud, deploy that build in those resources, run tests against those builds. Once those tests pass, to tear all of that infrastructure down and then to deploy into whatever environment I'm really going to be deploying into, whether that's a staging environment or a production environment or whatever environments I have in my pipelines, right? That's a very dynamic way of building applications, deploying applications, and managing those applications. And we'll see some more as we talk about cloud native development, what that really sort of translates into. There are some other parts of their definition from the Cloud Native Computing Foundation that I don't think are too prescriptive and not really fundamentally understanding the dynamic nature of computing itself, right? They talk about containers and service meshes and microservices and immutable infrastructure, right? And a lot of these exemplify the way that cloud native applications are built today, but I think it's a little myopic and short-sighted to believe that that's something that is going to be that way forever. As a matter of fact, if you've been following the news, you see over the last several months that leading proponents like AWS and Netflix have fundamentally started pulling back from some of the microservices and saying, hey, this works in certain scenarios, but in other scenarios, for other types of systems, that may not be the right approach, right? So fundamentally, I want to get away from talking about specific technologies and really talking more about the fundamental approach to building applications that are cloud native, right? So one of the fundamental baselines when we're building cloud native applications is to understand the idea of statelessness, right? If you think about a notebook, if I want 100 copies of this notebook, it's very easy if I take a brand new notebook to look at it, all the pages are the same. If I grab any 10 notebooks off the shelf, as long as they're the same model, if you will, or the same SKU of notebook, they're all going to be effectively identical. For my purposes of writing down notes, each one is as good as the other. The challenge comes when we start adding state to those notebooks. If I start taking notes in one of them and take a different set of notes in the second one, I can no longer just grab any notebook. I have to grab the one that's got the specific notes that I need, right? And this now sort of constrains me on which notebook I can use. And this state, i.e. the notes that I have stored in that notebook, now start presenting problems for me. If I've got 100 people that now need my notes, how do I get 100 copies with the right set of data for each individual, right? It's not as simple as just grabbing 100 notebooks off the shelf. I now have to figure out how I'm going to copy that data to all those different notebooks and make them available. So that state suddenly makes it unique. And now if I spill coffee on one or one gets thrown into the fire, am I losing data? Am I losing an important part of what it is that my application needs? Am I losing some information about what users were currently logged on and what their account balance was, whatever that looks like, right? Or whatever the application needs. So that state, we have to find different ways of keeping the state separate and apart from the actual compute and storage resources that we need, so that as I want to scale up or scale down, I'm not dependent, or I'm not somehow finding problems with that state and its ability to, or sort of the constraints it's putting on me in terms of that scaling, right? So one of the things we talk about in DevOps, or in this cloud native computing, is this concept of cattle, not pets. When we think about servers, and you go back to the 90s and prior years, when something happened to an application, say your Exchange server, you started having problems with email, you would call ops, or you'd call support and say, hey, something's going on with email. And they would go in the back room and they would sit there and baby this little server and say, oh, come on, I can get you to work. I can get you, everything's, let me see what configuration is. Oh, the hard drive's getting full. I need to go clear up some space on the hard drive, or maybe one of my hard drives in my Stripe set failed and now it's causing performance problems, or maybe I'm having some other hardware failure, and I'm going to have to go get a whole new server, hope I can recover state and move that to the new server. But I'm really focused on trying to salvage that one server, or those two servers that were running Exchange, whatever that configuration looked like, right? It was often funny when I started in computing, we often named our servers. Every server had a name, and they all had different purposes, but those names, like, they became pets to us, and every one was important, and we couldn't lose any single server, and we were attached to that physical hardware, because scaling was so hard, because I had to order servers weeks or months in advance of when I might need them, so I might not have another one on hand to just swap out with one of my pets. But in the cloud world, that's different. In the cloud world, we have redundancy in all of the resources we have access to. Adding a new compute unit into our resource pool is trivial today. I can do it in a matter of seconds from a command line, and not even bat an eye, right? As long as my account's in good standing and I'm paying my bill on time, I can just keep adding and adding resources as I need to. And so I don't worry about if one of those systems comes down when I'm building in a cloud native way. The system can take one of those resources down. Because they're stateless, every resource is exactly the same. Every resource is like that notebook that doesn't have notes in it. They're all equally adept at running and computing. They're all equally adept at storing data, or running whatever other resource I need run at the time, right? Whether that's data, whether that's CPU or GPU, whatever that looks like. So that redundancy, along with statelessness, is really the fundamental concept here, and where we think of these as cattle, right? Where any one cattle from the herd can provide the next dinner, or provide the next quart of milk, right? So the other major factor we talk about, which was resiliency, and this really goes to the fundamental core of that ability to spin up and spin down resources, the ability to have multiple resources serving requests sort of simultaneously, if you will, so that if one falls over or one part of the system goes down, we can pick that load back up on a secondary resource. So we used to do this when we started in DNN back in 2003, 2004, and built in web farm support. It was difficult because we often had to share state across that entire farm, and we had to keep state in sync across the entire farm. And we could configure farms of machines, but that might take minutes or hours to be able to do that, to add another node into the system. And we were ultimately, once we configured it, if we wanted to take it down, there was additionally effort in order to take it down and take a node out of the farm, right? And so if parts of the farm went down, it wasn't easy to recover. It was more resilient than a single node, but it wasn't truly resilient in the way we think about it in the cloud. Part of the reason, when you look at most of the clouds today, you will get a guarantee, an SLA of 99.9 or 99.95, and I think some of them are up to 4 nines, depending on what the service is and sort of how you've configured the system, whether you've got resiliency across zones or regions. And so what those start allowing you to do is for those additional resources to come online automatically, for the cloud to detect that there's a problem in the application or in the resource, to spin up other resources to automatically come online, even as they take a node offline, right? And we need to build our applications understanding that that's going to happen and could happen at any time. And in fact, if you go back maybe 2010, 2011 timeframe, there was some tools that AWS, as AWS was spinning up and really getting they were sort of a juggernaut at the time, but they had released a bunch of tools called the Chaos tool set, and one of those was a tool called Chaos Monkey. And the whole point of Chaos Monkey was to actually go in and help you test your systems, to test this ability to knock over resources in my application environment and see how my application responded, right? This was a way to test the resiliency of those applications just by saying, okay, we're going to take an EC2 instance offline. Okay, we're going to take this whole zone offline out of your storage, or we're going to take this region offline, whatever that unit is that I wanted to sort of test redundancy and resiliency around. So this is something that has been sort of baked into all of those cloud providers from very early on, was that we should be able to have a zone or a region go down in AWS and not care, right? Our application is built in a way that we understand that could happen. And the more we build applications that take advantage of that fundamental understanding, the better off we are, and the closer to that cloud native sort of aspiration we're going to be. So the Cloud Native Compute Foundation defined these 12 factors, or worked with the industry to define 12 factors on what they considered to be fundamental to cloud native computing. And the 12 factors fundamentally start with a code base that is under source control. And part of the reason for this is if we go back and think about the way I was talking earlier about the way we deploy our applications, it starts fundamentally from those changes in that source control, right? So that I could have this repeatable process that can quickly take that state of our source, build an application, deploy an application, and have all of that testing and deployment all happen in relatively real time, so that even if my entire application went down, even if all the resources completely went down, I could run my build service over again, or run my build pipeline over again, and completely redeploy my application. In fact, I've got a customer today that I'm working with where when I started working with the customer, they didn't have build pipelines set up. They were deploying everything manually. And what this meant was they were very much tied to the configuration of the VMs that they had in place. Just building out build pipelines meant that I could suddenly, just by pointing those pipelines to a different set of resources, I could spin up a whole new environment instance very quickly just by running my pipelines and saying, hey, instead of hitting this set of servers, go and hit this set of VMs instead. And now my application is up and running. Now that's a very gross way to allocate resources, because it required me in my current pipeline set to have a bunch of VMs dedicated. But fundamentally, there's no difference in that between having my pipeline spin up a new set of compute resources and spin up a new set of storage resources and spin up a new SQL instance inside Azure. All of that is scriptable, all of that is manageable, whether it's in Azure or AWS or Google Cloud. All of those things provide APIs that let me do that up and down and deploy those resources exactly when I need it. So the fundamental to this is why code base is such a critical part of this, and having that code base under source control and knowing exactly what the state of that code base is. The second part of this is around dependencies. So when you think about our applications today, we are used to having packaging systems like NPM, like NuGet, like Ruby Gems, or like Python pip and apt-get from for Linux, or WinGet on Windows, or Chocolatey if you're on Windows is another one. Brew if you're on Homebrew if you're on Apple devices, right? The key to all of these packaging systems is they give us the opportunity to explicitly declare what dependencies we have in our application in terms of packages that we need to build those applications. You look at systems like ARM templates for Azure. You look at things like a Terraform, which is another system that targets both Azure, targets AWS or Google Cloud, the various cloud platforms. And these are ways that we can define dependencies of resources. Exactly what type of compute resources do I need? What type of storage resources do I need? What type of specialized services do I need in these environments in order to run my application and to deploy my application? So all of those dependencies are defined and scripted and in a configuration file that allow us to easily and quickly redeploy resources, or to ensure that we have resources that are configured in a specific way. Configuration. This is one that I'm seeing we still have problems within the software industry, where applications have often secrets, passwords, or keys for applications or services that we need, and we often store those in some sort of configuration file, which that information is state, and that state ends up getting stored in our code base, which then makes that code base very fragile, because that state may need to change depending on what server or what environment we're deploying to. And so one of the things that we want is the ability to take the configuration out of that specific storage of code, right? Separate the code from our configuration so that we can attach configuration to different environments. And when I deploy into that environment, it already has the appropriate configuration. We already have secrets in that environment that are stored in a secure way that we're not going to leak those inadvertently, because we inadvertently stored a key of some sort inside our code base. And that got checked into a public repository, right? So if you look at like Microsoft Azure, the use of things like the Azure Key Vault, or the use of things like their app management or app configuration service. Those allow us to store configuration outside and separate from the application, so that even if an application goes down, when I redeploy resources, it can automatically pick up that configuration from the cloud and continue running. So again, we're starting to decouple that state out of the resource itself or out of the code base itself and put it in a separate place where we can tie that configuration to code at the point of deployment. So 4 is backing services. One of the things that we think about as we go into the cloud is the ability to treat resources not as something I need to deploy, but just something I can take advantage of at the point that it's needed. So if we think about my ability to get a Redis service or some sort of a caching service, right? I can spin that up in the cloud and I don't have to think about necessarily that service, or things like service buses or some of these other services which are not central to my application but are needed for my application to run. So we're going to have backing services in these cloud environments, and I'm going to be able to leverage them without having to explicitly go out and stand those up and do some of the configuration that we might have done in years past. And I may not even know how many resources are actually allocated to that Redis service, right? Like, I don't know how many CPUs are necessarily backing that Redis service. I might be able to tell you how much I/O that Redis cache has allocated to it, or I might be able to tell you how much storage that Redis cache has allocated to it. But I really don't care about the CPU allocation on that service as long as it's meeting its I/O SLA and it can store the amount of data that I need, right? So the 5th area here is about build, release, and run, which is how do I keep strict separation between when I build software, when I deploy software, and when I execute software. So if you look at most of the major platforms today for doing cloud native development, you will see clear distinctions between systems intended for building the software, and we might store that artifact of that build in some central location, or some sort of a repository, if you will. And then from that repository, we might pull those packages or pull those builds out just in time to do a deployment or release. And then finally, as part of that release process, we're going to have a separate environment in which we run everything. That release environment might have some build, or not build, some test configuration, some test execution that goes on as part of that release to validate that everything is going to work okay. And then finally, we deploy that and run that in a completely separate environment from how we built it, how we deployed it, right, and did that release. And then these processes, so processes being stateless, once again, back to that fundamental concept of how we scale, we start looking at, are my processes built in a way that I can scale parts of the system independent from each other? So I use stateless processes and I use isolated processes to sort of give me that scalability at the various points in the application. Port binding, often when we were running services or running systems internal to our network on our on-premise or even in a data center, we often had to think about, hey, how do I secure to make sure that my application can get access to SQL Server, but nobody outside the system can get access? And then as we look at cloud native, we start looking at, how do I set up virtual networks? How do I set up these virtualized environments that allow me to have very tight and strict control over who can get access to the application and where that occurs at, right? By by restricting what ports are available to what part of the network. And finally, here we look at concurrency. If I scale out, is my application built in a way that allows me to keep adding nodes to continue to scale? Often, if you look at applications from the early 2000s, they really didn't think about this, or they weren't built in a way that made them easy to scale, because we weren't thinking about building stateless compute systems. State was very heavily tied in with our compute. And so as a result, we couldn't really run concurrently across multiple nodes. There were too many dependencies. Or we might have data or computations that had serialized restrictions, i.e., I had to do a certain calculation in one part of the system before I could do the next calculation, before I could do the next. So if you start looking at systems like Hadoop for running these very large concurrent data processing processes, that whole MapReduce ability of systems like Hadoop allow us to run very, very large data processing jobs across a large cluster, and to do so in a very concurrent manner. Disposability. Here we're talking about our ability to start new resources quickly and dispose of them equally as quickly, right? This speaks directly to that elasticity we talked about earlier. And can your application handle nodes coming online and going offline in a very fast manner, right? Does your application care how many nodes are in the system? And are we building in a way that gives us the flexibility to add and remove nodes at will? Dev prod parity, right? So part of the cloud advantage that we have is that I can build multiple systems that have equal access to resources, i.e., they're almost virtually identical in every way, because I have in those earlier configurations that we talked about, I can configure systems and say, this is exactly what my production system needs to look like. And I can take that same template for how to deploy in a production. I can make a copy of it and say, okay, instead of being production, this is going to be stage, right? And now I can deploy into that environment as well. And I know that it's set up exactly the same as what's in production. And I can create a dev environment that is almost the same. Maybe I give it lower level CPU resources. Maybe I give it a little less storage, but I know exactly that I need X number of CPU or nodes. I need X number of storage nodes or Redis caches or whatever that other resource looks like, right? And I can keep as much parity as I want between different environments, all back to that configuration we talked about earlier. Cloud systems generate a lot of logs, right? In years past, when we had those finite resources on-prem, on our servers, we used to keep logs, but we often did things like rolling logs, where we might keep some logs, very detailed logs, down to the minute, down to the second, down to the millisecond, and we would keep those, and those were very large. So after a day, we might only keep part of that log data. After a week, it might get sparser yet. After a month, it would get even more sparse. And over the course of a year, you start going back to these larger and larger chunks of time, and we keep less and less of that data. That's less of a problem today in the cloud because of the massive amount of storage that we have available to us in the cloud. And so we can treat logs as this resource where we can keep as much or as little as we want. And because of those capabilities, we now have the ability to start streaming more and more data in real time. If you start looking at systems like Spark and some of the other systems, Event Hubs, and others that are ingesting massive amounts of data and just dumping it into giant data lakes. The ability to do that with everything, with our application logs, with our system logs, with our telemetry data, with our application monitoring data, right? All of this stuff can just go into this massive data lake, and we can use other background systems to consume and digest that data and spit out meaningful information to us. And those are systems that just weren't readily available to most application developers, even as recently as 10, 15 years ago. And then finally, the last area is around admin processes. Because we have the ability to spin up large and small compute resources within the cloud, it's very possible to create customized one-off admin processes and tasks that might run as a function, or that might run in a cloud shell as a singular command line instruction in the cloud shell, or on a local system connected remotely over SSH or some other remote protocol to execute some task in the cloud and kick that off and run some process in real time. We don't necessarily have to embed all of that administrative capability directly into our application. When we were on-prem deploying or running applications against our production environment was something we didn't do because we had limited compute, limited bandwidth, limited storage. So we often shied away from running services and running things in those environments. In the cloud, we don't have those same restrictions. So we don't necessarily have to deploy all of our code directly in the primary application or in the microservices, if you will. We can have command line apps that do very specialized admin tasks and just run them as needed and spin up the cloud resources as needed to run that task against our database, against our files, against our applications, our running applications to monitor those, whatever that looks like for you, for your admin processes. So these are really the 12 factors when we talk about cloud native computing. This is really what, and cloud native applications, these are really sort of those 12 factors that we look at to determine, are you really building in a cloud native way? Are you thinking about these 12 areas of your application and how they're going to impact the way that you build that application? Because fundamentally, these are things that were very difficult to do for many systems running in those on-premise data center-based applications that we built 10, 15 years ago, 20 years ago. So I don't know why that's saying end. Maybe I've got something hidden down here. Let me, where did that go? This is hidden. Nope. No, let me just jump to that slide, sorry. Oh, wow. For some reason, it's not giving me all of my slides that I have available. Don't do that. No, it's here. We'll just do this the old-fashioned way. We'll scoot this over, and I will just pull it up here. So a couple of resources to point out here. You can get, and I'll make a copy of these slides available after the talk. I'll put them up on SlideShare and also submit provide them to GlugNet, and they can post links to these. But if you look the cloud native .NET applications for Azure, there's a great link there that Microsoft talks about from an Azure architect perspective, what that might look like. Again, link to the 12-factor apps and what that looks like, cloud native computing. I do use a lot of photos from Unsplash, so shout out to them for a great service that they provide. If you ever need access to resources, images for, especially for presentations, I use it a lot, but Unsplash is a great resource. And again, improving, we have a lot of great resources at improving. If you ever have a problem, we're more than happy to help in whatever way we can. From a community perspective, we do a lot in the community. Part of the reason I'm here speaking tonight is because we believe strongly in supporting community, and this is part of our community outreach effort. And we have people who are speaking all over the country or in conferences and user groups. So anyway, and then finally, if why is this not showing? Oh, somehow I think, no. Did I get, I'm missing slideshow. Let me see if I can just go to the next. I don't know if it's going to let me go to the next slide. There we go. Yeah, so for those who still didn't get this earlier, if you want to register for the card, I'll leave that up. Thanks everyone for joining me tonight. Hope you got something out of the talk, and I appreciate Stephen and Joe for inviting me to speak here this week. And anytime you guys want me back, happy to come speak on a variety of topics.
All right. Thank you so much, Joe. Are there any questions?
Joe, I have a question.
Yes.
You mentioned, this is Joe Kunk. You mentioned in your presentation about Netflix, and I think the other major vendor was Team City, who have blog posts that talk about how they actually saved a considerable amount of money by moving their production compute resources off the cloud and back internal. And I'm not that I'm saying that that's the best way to go, but
yeah,
as you said, it's an individual thing, right? It depends on the situation. Right. If you're planning a cloud environment today, and knowing that the cloud environment in a full production end situation may not be the most economical, how do you balance those two concerns in your architecture?
I'm not sure I fully understand the balancing act you're trying to do. What size organization are we talking about? Is it a small organization or a large organization? By large, I mean tens of thousands of people in the organization.
That's a good question. I would imagine that scenario would be more applicable to a large client base as opposed to a small.
Because yeah, so here's the fundamental thing to understand about the cloud and where people make decisions, I think, in part out of a lack of knowledge and understanding about how the cloud is constructed. They think that I've got a server in the back room and somehow that's equivalent to a unit of compute in the cloud. And fundamentally, the two are miles and miles apart, right? Because the thing that compute unit in cloud has that server in my back room doesn't is it's got a security specialist, it's got a network engineering specialist, it's got an up-to-date operating system, it's got people who are looking at intrusion detection and other application monitoring or system monitoring services in place. And all of that sort of comes, I won't say for free, but sort of comes with that single computing resource that's in the cloud. That ability for that thing to scale or to be resilient is something that I can't compare what I get in an on-prem server with what I'm getting in the cloud. Now, the way that companies get around that, when you talk about a company like Microsoft or like AWS or like Netflix or some of these very, very large organizations who have massive IT teams, right? They already have network engineers. They already have Windows or Linux or Unix security specialists, right? They already have a lot of this capability in their um, IT staffing within that organization, right? So they don't have to go out and hire an entire operations team because they already have built that system out. They already built those costs out. And so, yes, they're able to build out very robust systems, right? Like you look at Netflix. Netflix is not, they have some stuff in the cloud, but they run a lot of stuff in their own data centers on their own networks, but they've effectively built their own cloud systems because they have the resources available from a personnel perspective to be able to enable them to do that. Most organizations, even 50, 100 million, 200 million, billion-dollar organizations do not have that level of specialization in terms of knowledge in their IT group to be able to support the same capability they might in the cloud. So when you say, yes, I could do this on-prem or I could do this in the cloud, and on-prem I might throw 5 servers, 10 servers, 100 servers in there, right? And it's like, what are all those hidden costs that you're not thinking about? The cost of the entire IT group you now have to account for to provide that same level of service and support.
Okay, so obviously one net effect of what you just said is for a smaller company, it will likely never make sense to try to bring it back in-house, right? It only makes sense for those companies that are large enough and fortunate enough to have deep IT support.
Right, because right, like I know that I can go to sleep at night with my application running on Azure and know that if Azure goes down, there is an entire team of people at Microsoft who are working to bring Azure back online, whether I'm awake or not. If I've got my system running in a data center, which we did early on in DNN, when that data center had a problem or my application had a problem, right? I was the one up at 3 a.m. getting the call like, hey, we got to get this back up. And often that was late nights or long nights or weekends, whatever it took to get the system back up, right? Because something happened to one of our servers. And so that there are things that happen in any compute system that you just can't account for. A network card goes out, a freaking uninterruptible power supply gets interrupted.
Mm-hmm.
And right, so those things are not things that I worry about when I have my applications running in the cloud. And yes, I pay a little bit more for that service, but again, it comes back to that unit of scale that I have in the cloud versus what I might have on-prem. And part of that unit of scale is, do I have enough work to keep a cloud engineer or to keep a network engineer busy? Do I have enough work to keep a support team busy, right? Can I just add another support person on this week because I'm getting too many calls? Probably not. But if I'm in the cloud, there's massive number of support people at those cloud providers that are constantly on call 24/7, 365. Doesn't matter that it was the 4th of July. Somebody is going to be there to pick up the phone, right?
Mm-hmm. Good point.
So,
thank you.
Yeah, all of those things, right? Like money solves a lot of problems for organizations, and it's just, where are you putting the money? Are you putting the money in buying a compute unit from Azure, where the next time I need another compute, it's like, okay, here's another $20, here's another $100, whatever. Or are you buying a whole new server and having to invest another $50,000 chunk, having to buy another network engineer at another $150,000 or $200,000 for a high-end network engineer to, because we've just scaled and one guy can't do it anymore, and I've got to add another unit, right? So those are the sorts of decisions you have to look at. Is that $200,000 network engineer, is that a trivial decision because I'm a $10 billion company, or is that a big decision because I'm a $50 million company and our margins are really tight?
Okay. All right. Thank you. That answers my question very well.
All right. So not hearing any more questions, I think we can go and wrap up. So I've dropped the link to the survey in the chat there. I will also email that out in case you happen to miss it in the chat window. I will leave that open for about 24 hours, at which point I'll summarize everything up and get that summary off to you, Joe.
Okay, awesome. Well, thank you very much, Stu.
All right. Thank you again for speaking to us, and have a great night, everybody.
Thanks.